This
Also
conference will now be recorded.
went out to Fairbanks, had a very interesting trip, middle of winter, which is not too bad. I'm speaking to you from Calgary, Alberta. So I'm a retired mechanical electrical engineering consultant from Calgary, cut my teeth on deep green institutional buildings for the last 25 years. I've been retired for 2 years. But today I'm speaking to you in my capacity as a member of the Building Ad Hoc Committee for the new ASHRAE Headquarters. So I'm also, I'm not sure if I mentioned, I'm also ASHRAE Vice President currently, representing our region, Region 11. Proud to do that. So let me just go up one. Okay. So the new ASHRAE Headquarters, something that, let me just collapse this. Okay. So it's really a story about an office building getting a new life, and let's go through what that really means. The subcommittee included myself. It was then current chapter or society president Daryl Boyce. Ginger Scoggins was a chair. She's basically all of us are kind of ASHRAE heavy duty groupies, and as well included was Jeff Littleton, our executive director. I also chaired a technical advisory subcommittee, and I'll talk a little bit about what that subcommittee did for the project. So for those of you who don't know, our ASHRAE headquarters that we had been in for the last 20 some years, and it was added to about 10 years ago. I guess it was more like 30 years we were in it, was a LEED Platinum building, 2 stories, located in a suburb of Atlanta. And what started this whole affair is gradually in the neighborhood of this office, a large healthcare company started to buy up properties with the plans of creating a healthcare campus in the area. And by the time they had finished buying all the properties, our property was the only one left. And although we didn't intend to sell out to them, they kind of made it fortuitous for us to think about it. And 3 real reasons. Number one, our existing headquarters was very tight as far as people were concerned. They were sandwiched in there really tight, not a lot of square footage per employee, so it wasn't a great workspace. The area around the office was destined to be right across the parking lot from our head office, is where they planned to put the energy plant for this new healthcare campus. So a huge energy plant across the campus, lots of noise, potentially pollutants. So that was one thing they did. And then the other thing is they have really deep pockets, so they're prepared to offer us a very good price for our office in a heated up real estate market. So looking at all of that, the leadership at ASHRAE considered our options, and we didn't really want to live across from an energy center, so we decided to move. We looked at a few things. We looked at maybe leasing new space. We looked at design building new space. We looked at building from scratch, not design build. And in the end, we decided to show a good example of what is a major issue in our industry, and that is renovating existing buildings and bringing them up to good standards. And so we know right now that 72% of the floor stock in the US belongs to buildings over 20 years old. And if we could renovate a 1970s building to a high performance net zero ready facility, we'd have a good example to set for the rest of the industry and for our members. So we use that as our policy going forward and our inspiration, and started looking around for what we could do. Having said that, ASHRAE or Atlanta was very heated market. We redid program for the building and found that we did indeed need new floor space, about 10,000 more square feet than what we currently had to house our people. And one of the things that happened as we looked around the market was it was pretty tight on buildings we could find. And so we didn't have a whole lot of choice out there. We did find a building that in the end we purchased, but it was significantly more than what we needed. We purchased something that was almost 67,000 square feet. We only needed a gross area of 44,000 square feet. And so while we didn't develop all the area in the new building, it did affect our budget because renovating a 66,000 square foot building rather than something closer to 44 caused some budget issues for sure. So the new headquarters is located in a city on the outskirts of ASHRAE, about 10 miles further out from the airport, from the existing headquarters called Peachtree Corners, 66,000 square feet on 3 stories, built in the 70s and purchased in December of 2018. So we very quickly decided to come up with our owner project requirements. So we wrote a document, and that was really my subcommittee's work task, was to write an OPR, or owner's project requirements, for the document. And we had some mission critical items, the usual stuff: affordability, safety, of course, complying to our standards. We wanted to do something special with acoustics because we know that's the major complaint area for office buildings. And we wanted to set a lofty goal of net zero energy ready, which required some pretty low energy utilization factors. So the OPR highlighted a whole bunch of things. It was quite a lengthy document and talked about a whole bunch of requirements, but some of the major ones is we wanted to exceed our requirements for ASHRAE 189.1, which is our green building standard. So we wanted it to be a green building. We obviously wanted it to be very energy efficient, trying to go for net zero. So the initial EUI we set of 21.4 kilobTUs per square foot per year, that is the recommendation that comes out of the advanced energy design guides that ASHRAE produces together with AIA and IEEE and Department of Energy for different buildings. And we have a AEDG, Advanced Energy Design Guide, for medium and small office buildings to take them to net zero. And that requirement in Atlanta requires a 21.4 EUI. We actually thought we could do a lot better than that. So we set a stretch goal of 15 EUI. Wanted it energy efficient. We needed daytime plug loads that were very low to make sure that we could meet zero energy. And we set a 3.3 to 5 NC RNC reduction on internal noise for acoustics. It's amazing how few office building acoustic standard documents there are out there. So we used the General Service Administration acoustic guides as our guidelines and wanted to improve on those. We went to 1.3 times the outdoor air rate, which is what we have in our existing headquarters and what often is a goal for green buildings out there in the industry. Demand control ventilation in high octa spaces. A lot of daylighting, generous daylighting, 55% of the time in regularly occupied areas. And we wanted to look at resiliency as part of the OPR as well. Our schedule constraint really boiled down to an occupancy in October of 2020. That was based on when the hospital group wanted to take occupancy of our headquarters. It's something we negotiated based on allowing ourselves a tight but reasonable design and construction schedule. So how do we achieve our project goals? We set the construction budget quite early. That was a bit of a problem because we set it before we knew we bought an oversized building. So in the end, our budget wasn't adequate, and I'll show you how that shook out at the end of the presentation. We set our move out date of October. we set our project criteria by writing an OPR and having that ready for the design team to look at, design and project management teams and construction teams to look at during their hiring. And then we went on to hire the right team. One of the things we had to decide quite early is how to execute the project. So the Atlanta construction area, construction atmosphere was very heated up. And so it wasn't seen that it was practical to get too innovative on the delivery of the building as far as construction goes, because we wouldn't get any bidders interested, because it had to be a clean project in order to interest people in building the building. So we ended up deciding to utilize a project manager. We went to an outside project manager because we didn't have any on staff, and we needed day-to-day management of the design and construction team. So we developed an RFQ and hired a project manager. We then decided with the project manager for project delivery, integrated project delivery, which is kind of an innovative risk-based approach that didn't interest a lot of people in Atlanta. They weren't familiar with that. So in the end, we decided a construction manager at risk. We wanted early contractor involvement, and again, did not want to scare away interested bidders. And then we hired a project team. We hired an architect and engineer in one swoop. So the engineers joined the architects' teams. And in the end, we got quite good interest from very innovative architectural engineering teams from across the US. This was a very high profile project and quite innovative in Atlanta, going for net zero energy. Not a lot of buildings in Atlanta are going that hard on green and energy. Here's a shot from Google Earth on the site. So you see the building there has got two main blocks separated by a central barrel vault atrium. We've got lots of parking for over 200 cars, even though our staff is less than about 140. We've got a parking area with deliveries to the left on the picture, and on the right we've got an entrance into the lower level of the building, and to the top of the page we have the main entrance into the building with parking. We have a bit of a storm pond / lake. I wouldn't, it's a bit of a stretch to call it a lake. I'd say it's more of a slough or a storm pond. It's surrounded by a number of different owners. We did not have rights to the lake though, so we couldn't use it as a water source, heat pump source of any sort. There's kind of a quick SketchUp model of the building. You see the barrel vault, very 1970s design, strip windows around the perimeter. We've got a top above grade level. We've got a middle level that is sort of buried into the ground to the north and has some solid walls, and then a service basement, partial basement with some lookout to the lake to the south. After we cleaned out all of the existing structure on the upper level, we're left with a couple of cores and that central atrium and 2 blocks of unequal sized office areas available for development. On the lower level, the same sort of thing. You know, not the greatest building. It's got these strip windows, floor to ceiling, a lot of glazing, 79% window wall ratio. Infrared shows the glazing was very poor, double glazed, poor frames, old aluminum Conair product. So that opened up a couple of discussions on things. I didn't realize, coming from Calgary, you know, too much about Atlanta. I knew it was hot and humid, but we did quite a bit of extensive looking at the climate. And these graphs on to the right showed us a few things. It showed us that, number one, if we wanted to get a deep green building that we could naturally ventilate and maybe use nighttime purge cooling or anything innovative like that, it wasn't going to happen in Atlanta. Number one, it's too humid. Number two, we just don't get the decrease in temperature at night that we need to be able to do that. We did look at the winter side of things, not very not very cold at winter, but oddly enough, a few cold snaps that cause some pretty large peak heating loads. So envelope is important. One of the more important things in Atlanta is infiltration. Because of humidity control, letting that moist air either into the envelope or through the envelope and to load down the building is just a bad idea. And so to get a very high performance building into Atlanta, you really do have to control the infiltration big time. Almost more crucial than it is in our cold climates, just because of the moisture damage that can happen on the envelope if you start getting mold buildup in that climate. So we wanted to define some optimum areas. So one thing we knew we wanted to do was look at the window wall ratios. That existing 79% window wall ratio lets out a lot of heat and lets in a lot of solar. And so we wanted to balance that off against daylighting. And then we also wanted to balance it off against thermal loads. And so the window wall ratio, the air infiltration, and the insulation values of the envelope were pretty important. Important enough that we did some envelope sensitivity analysis to get us where we wanted to go. We compared the envelope existing performance with ASHRAE 90.1 2016, and then we also did some sensitivity analysis with energy modeling and determined what recommended R values were. And you can see that our R values are significantly higher, R17 versus R8, 90.1 for the walls, for the roof, 35 versus 25. For window assemblies, we stayed with the same solar heat gain coefficient, but went with energy efficient triple glazing windows. We reduced the window wall ratio to well, about the same as ASHRAE 90.1, but way down from its existing 79% value. Looked at some shading, and you can see that infiltration value, you know, a quarter of what ASHRAE recommends for 90.1 is what we thought we had to reduce it down to in order to get down to net zero. You can see that the ASHRAE Energy Design Guide for net zero energy recommends a 15.6 R value for climate zone 3. So we're looking at even better values than that R17. We also looked at daylighting, very important factor in net zero energy buildings, and also building a building that's got great indoor environmental quality. So you can see the bottom there as we modeled it with the existing lighting. Daylighting was pretty bad, highly shaded glazing, lots of it, but not letting a lot of daylighting in. So we looked at ways on how we could increase the daylighting into the space. In the end, we looked at raising the head of windows up, providing a little bit better spacing on the windows, and adding skylights for those deeper floor plates where we could get some daylighting interjected into the interior of the floor pan. In the end, we had to balance all those out and came up with window wall ratios looking east and west of around a third or 33%, north and south of 42%, and that's way down from that existing 80%, and that's 79.9% that we had. So those are the new windows. You can see that those windows are showing as being operable windows. In the end, we went to a hermetically sealed box, no operable windows. The premium for providing operable windows in the Atlanta market are quite staggering. You know, in Europe, when you specify operable windows, it's almost an extra not to get them operable. But in Atlanta, it was a huge number to go to operable windows. So once we had decided on our high performance envelope, we started doing some energy modeling on mechanical systems and other strategies like the daylighting and the external shades and whatnot. So there's sort of where our recommended envelope ended up to, and then we started in on doing performance analysis on different things. The first one we wanted to nail down was the daylighting strategies. And so the end, we optimized on 18 skylights on the top floor, no light wells down into the middle floor. So the middle floor has significantly less daylighting than the upper floor. We've, of course, gone to 70% daylighting in the work areas on the top floor, so that's really good. And then started laying out the furniture so that they could take advantage of how the daylight enters a space, and so that the partitions and the height of the partitions in the workspaces weren't cutting down on that valuable daylight. So in the end, 57% of the regularly occupied spaces use daylight above 300 lux, so that's quite a bit above our minimum requirements. So we did good on that level, and the level on the lower level wasn't as great, very similar to the top level, but not as deep a penetration. So the path to net zero, as you put in a better envelope, and we looked at natural ventilation. In the end, I said we didn't go with it. Then we start looking at the HVAC. So it was interesting in this building that there was two design teams from this mechanical company that were looking at proposed buildings. One was from the company's San Francisco office, and one was from their Atlanta office. And they came up in the end with two proposed mechanical systems that sort of floated to the top for consideration. The first one was what would be called the East Coast system fondly. And this was an all air system. It used a series of about 20 small all air heat pump systems sitting on the roof. So a bunch of rooftop units serving different zones. And these zones would be equipped with actuated thermofusers or actuated diffusers to give you zone control. But there were basically a whole bunch of separate little air cooled heat pumps. They still showed the operable windows, but these operable windows didn't make it into the design. But they also showed some whirlybird fans or some large volume, low velocity fans, kind of big ass Heiku fans operating in the space to mix up the space, distribute the air, and help widen the comfort conditions in the space by providing a little bit more draft. So when you provide these fans properly designed in the space, it allows you to raise the summer set point in the space because of the draft cooling. So that was one system. The other system was a hydronic system, fondly called the West Coast system. And so this system is I'm very familiar with it, and part of the reason I supported selection of this design team, because I thought personally this was a great system to try on the headquarters. It really consisted of dedicated outside air systems supplying fresh air to the building through dedicated outdoor air ductwork system, and then terminal units of radiant heating and cooling panels installed at the ceiling in islands, floating as acoustic islands floating in the ceiling. And then again, those Heiku fans that provide that additional airflow. And the Heiku fans were being designed in such a way that they could also increase the convection off of the radiant panels to get a little bit more output off the radiant panels. And then to supply the chilled water and the hot water for the radiant panels, we were looking at a water source heat pump system sitting outside with several options on how to use a condenser system for that. You show in that diagram there that it's air cooled, but they also looked at water cooled with a cooling tower and also looked at geothermal. So as we go through these energy models, this one showed a recommended envelope and an optional stratified program. That stratified program was collecting different parts of the program or the employees in the space in various areas so that large parts of the office could be shut down in different times of the day. For instance, if the learning center wasn't being used, or if certain departments were going home. That in the end turned out to not be a good option, so that one was dropped. But what this graphic does show you is the difference between the all air system and the chilled water radiant panel system. So you can see that the West Coast system, the radiant water system, was more efficient than than the all-air system, but not by a whole lot. When we started to dig into it a whole lot more, it turned out that that gap started to widen. So the harder they looked at the air system versus the water system looked better and better, and the air system actually worked worse and worse. So that gap ended up being more like about 5 rather than just 1.1 that you see there. Because in the end, what we wanted to do is we wanted to select this hydronic system. It provided a bunch of improvements and advantages that we saw as a committee. The first one was better indoor environmental quality. It was going to be a quieter system than the all-air system. It was going to provide better ventilation effectiveness. It was going to provide better thermal comfort because of the tighter zoning that you could get with radiant, and also the fact that radiant provides a much more comfortable space than non-radiant systems. We thought that also, a whole bunch of rooftop units wasn't exactly showing best in class system selection from an international organization like ASHRAE. Funny enough, though, the air system was significantly cheaper it was significantly cheaper in Atlanta than it was in our part of the world. So I come from Calgary, where this water system has been used a lot. And it ends up being cheaper than an all-air system because piping and pipe work goes in much cheaper than tin work in our part of the country. But in Atlanta, it's the other way around. Pipe work is very expensive to put in, whereas tin work goes in ultimately very cheap. Part of the reason for that is the unions, or even the non-unions, and that much of the piping that would go in this building when it went in Calgary, for instance, would be done by plumbers and apprentice plumbers because it's mostly brazing work and soldering work. Whereas in Atlanta, they really don't have those trades well developed. And so pipe fitters would normally put this piping in a building in Atlanta, which makes it extremely expensive. So the all-air system was coming in quite a bit less expensive than the radiant. It took us several meetings with contractors to get them up to speed on just how easy these radiant systems go in, for them to start lowering their price and get rid of some of the risk pricing in it. And in the end, it turned out to be about a $200,000 to $250,000 premium to go to the West Coast system, the system you see in front of you. So this system has got a modular outdoor air-cooled heat pump. It's serving a heating loop primary and a cooling loop primary that uses a buffer tank just to make sure that there's enough volume in the system to give good control on the heat pump and stop too much cycling. Then both the heating and cooling are fed through secondary cooling and heating loops out to the devices. And there's several different devices. There's the radiant panels, which are served two ways. One way is, for some of the radiant panels are cooling only panels. They serve the interior of the building only, always in cooling mode. So they just use two-way valves. In much of the building, though, the panels are used both for heating and cooling. And so we used 6-way valves out of Europe that allow you to feed either cooling or heating without any chance of crossover, even under failure mode. Between the heating and cooling loops. And in areas where we were serving a good deal of radiant panels, we served them through radiant floor manifolds up in the ceiling. So just a way of zoning the panels so that you can get good balanced flow to the panels. We use manifolds. In some areas of the building, in the basement, for instance, we used water source heat pumps. So we used a little loop pump off of the return water from the radiant panels to serve as a condenser loop for the heat pumps serving the building. And so it's a heat recovery heat pump system, air cooled. We looked at some other ways of doing it. Number one was ground source, but the premium versus the energy saved was just not there. There's virtually no energy saved in this climate for the heat pump system versus air cooled, and the premium was quite staggering for again ground source system, which isn't that common in the Atlanta area. On the air side, we've got a dedicated outside air system that serves a whole bunch of supply air valves, and within the system, the outdoor air comes in, it's pre-filtered and final filtered, goes through a heat wheel, enthalpy wheel, then goes through a heat pump system that uses reheat to reheat the air back up. So we subcool the air, reheat it back up again to take out the humidity, and then supply it to the space. We collect the space through exhaust air valves through a pre-filter, take it through that heat recovery wheel and out of the building. So that's sort of on the air side. We have 2 DOS units like this, dedicated outside air systems in the building. So if you look at some of our spaces, there's a couple of classrooms we have where we've got perimeter heat cool panels, interior cooling only panels. The perimeter is served by the 6-way valve. The interior is served by 2-way valves. And those deliver heating and cooling to the space. In the classroom areas, we deliver the fresh air displacement ventilation style, low velocity down low at the floor and allow it to filter through the space, increases ventilation effectiveness and contributes more to the cooling. In all the other spaces in the building, basically we deliver the outside air at the ceiling and let it get mixed in with the fan air that's coming off of the Heiku fans and delivered to the space. So a little bit different air distribution, but in both cases, they come from the same DOS units at essentially 65 degrees Celsius temperature, 64 degrees Celsius temperature. So they don't provide a huge amount of the cooling when they're delivered at the ceiling. In the open office areas, we've got these floating islands of radiant panels. Ventilation is delivered basically a pretty neutral air temperature, just a few degrees cooler than room temperature. So they don't provide a lot of temperature control in the space. All the temperature control is with the radiant panels. So the radiant panels are piped up with exposed rigid piping. We only insulate the supply piping. We've got duct distribution that delivers air either through diffusers or through some fabric ductwork in some of the open areas. And then those ceiling fans increase the mixing and induce the capacity on the panels. All quick connects on the panels. The panels are supplied out of a supplier out of Canada and one of our sponsors for the building. In the open office areas, there's the floating panels, heat cool panels because of all the glazing. And they're served from those 6-way valves and the radiant panel manifolds. One manifold for collecting the return and one manifold for supplying the supply. And you can see those Heiku fans, the way they're located under the panels, they actually suck the air and blow the air up onto the panels in the summer to increase that convection off the panels. So as we got through the net zero discussion, we ended up getting the high performance HVAC, adding the lighting and daylighting, considering the plug control, and that started getting us well under the 21.4 target and towards our stretch target of 15. Right now, our modeling isn't completely done. The consultants are working on it, but it's looking like they're around 17 to 18 on the energy use index. So that's pretty good, about halfway between our stretch target and our minimum target that we had set. That's kind of the finished floor plate. The upper level has included those colored meeting spaces and then open office areas and some closed offices for the staff directors. The middle level, it's got that large training room at the north where it doesn't have any daylighting into it. That's where it backs up onto into the dirt. We've got some meeting rooms as well, and then we've got some beautiful south-facing classrooms that face out onto the lake. You'll see that checkered area off the end of the atrium is a deck that is a very nice amenity for the staff. They can go out onto that deck for lunch and look out over onto the lake. So a very nice office. We've got the basement area where storage has allowed us, excess storage has allowed us to bring offsite storage back onsite and save some money for no more offsite storage on some areas, allows us to to distribute some product out of this building. And we have a rather large mechanical room that's basically got the water heaters in there and the pumping systems and that buffer tanks. So there you can see the construction proceeding there. They're just starting to frame up some of the interior partitions, looking at that old concrete framed structure. There's the front entrance going in where you've got a bridge across to now an atrium that does not include a barrel vault. So we replaced the roof on the atrium, got rid of that energy efficient barrel vault, and have got a beautiful entrance coming in. Octagon shaped lights looking out onto the lake at the back and the deck. We've got a beautiful walkway on the incoming side. That's the main entrance into the building. Some interior spaces. There's one space with the radiant panels at the ceiling. You can see them as a slightly different gray than the ceiling tiles. They're punched with holes, so they provide acoustic absorption as well. And you've got the Heiku fan. There's a space that does not have a Heiku fan, but it's got the radiant panels. There's the main classroom. So in the classroom, this is the one of the rooms that has displacement ventilation. So the air is distributed out at the floor around the perimeter of the room. And then we've got the radiant panels at the ceiling providing the heating and the cooling. Some circulation areas. Main lobby looking back towards, actually this is the lobby and coffee cafe space in the basement, looking out onto a basement area. So that is underneath, if you look forward, that space that you're looking at outside the doors is underneath the bridge where you enter the building. And that's a nice little shaded area where people can take a break. And behind the camera, behind those steps there is the patio that you see right there. You can see there's a nice path that the city of Peachtree Corners has built around the lake to allow for walking at noon hour or jogging around the lake. Funny enough, one of the things we looked at adding to the headquarters was a fitness center. And in the end, the staff overwhelmingly said, no, we wouldn't use it anyways. We just don't work out. We don't work out at the office. We work out at home. And so all we need is to take lunch and have a walk, but no big workout room. There's the open office areas. You can see the new windows. They are still floor to ceiling in this area, but there's a lot less of them. And the daylight penetration is pretty good in this space. You can see some of the piping exposed. You can even see one of the manifolds there, served off of the 6-way piping system. We've got the piping running outside to a remote air-cooled heat pump that's coming out near the loading dock area. And to the right, what presentation wouldn't be complete without a beautiful mechanical room. So that's our mechanical room right there. There's a look up at the deck and showing some of the shading on the glazing and a lower walkway area that is part of the basement that allows you to get from the east side to the west side. Funny enough, without that walkway, you have to go up a floor, over and down a floor to be able to get to the two sides of the basement. Not very practical. There's also 2 elevators. One elevator serves the top level to the middle level, and that's a passenger elevator. There's another elevator that serves the middle level to the basement level, but the elevator doesn't serve all 3 floors. We looked at trying to correct that during budget. We just couldn't afford to do it, so we've left the 2 elevators in place and just gave a tarting up to the 1 passenger elevator. So the last thing I wanted to talk to you about was the next step to net zero energy, and that is looking at the photovoltaics or renewable energy for the site. So you see the site there, it's got a rather prohibitive feature to it, and that is a petroleum pipeline, that right-of-way that runs right through the site. So what that means is we can't install anything other than pavement over top of those pipelines. That kind of reduced where we could put photovoltaics, and it reduced also what we could do on the site as far as even trenching across that pipe right of way for new electrical, for instance. You can see though that it's also a fairly heavily treed site if you remember that Google map. So we had to think hard and long about where to put photovoltaics. In the end, we went to a hybrid solution. We put as many PVs as we could on the roof of the building. And you can see a model there showing the destined rooftop system of PVs. And then we had to take some of the parking that we no longer needed and just populate radiant PV panels in the parking lot. And then in a landscape area where the trees weren't too large, we were allowed to remove some of the trees off of the site without getting too heavily into development permits and put some PV in. So when we put this PV system in place, it's about 250 kilowatts of output. That is the maximum we could put in because we were capped by Georgia Power for net metering, so we're limited to that. That'll get us very close to net zero energy, but kind of not as much as we would like, but in a stretch, we think we can get to net zero energy depending on how they run the building. And the cost of it was about $550,000 or $500,000. The DC size of it is 331 kilowatts. You can see the difference between capacity and output given inverters and efficiencies and all of that sort of thing. So we're hoping this contract has been let. They're busy working on it. They'll start installing in about 3 weeks, and in about a month and a half, the system should be properly installed. So our original budget, before we knew that we were buying a 66,000 square foot, or sorry, a 66,000 square foot building instead of 44, 45, was around 15, 16 million. In the end, we had to come back to the Board of Governors and ask for more money twice. Once when we decided to do some renovations on the envelope, and then the next one to account for basically the heated up construction market in Atlanta, which just continued to heat up over the 18-month design period. And then on top of this is our $500,000 PV. The good news is that through a capital campaign for raising money, we've raised almost all the money necessary to build this headquarters. We're looking at less than $2 million that ASHRAE had to come up with through the general operating fund and through a loan to pay for the rest of this. So thanks to the generosity of both the suppliers supplying equipment and services in kind and providing cash, we have done phenomenally well in developing this headquarters for a minimal cost. So I would be remiss in not reminding you that this is your building is ASHRAE members. And so if you find yourself in the Atlanta area, there is a standing invite for you to drop by and see the headquarters. Right now, they are minimally manning the headquarters. About a quarter of the staff are in there, splitting the time during the week. Most people are still working from home, understandably, but when the building is occupied after COVID settles down, more than welcome to come by anytime you want and either work temporarily out of the building, visit the building, tour the building, whatever you want to do. It's your building. Those are the design teams and construction managers that were involved in the project and did a great job, and would be remiss in not thanking them for their input and also some of them for their donations. With that, I think I've finished in time to be able to, so we got about 12 minutes or so for questions and answers if you want, or not, whatever you want.
Thank you, Tim. Thank you for your time. Let me see if there's any questions in the chat box. Seen anything?
Anyone voice a question? Anyone want to just turn their mic on and ask a question? Go ahead.
Yes, this is Dave Shumway with AMC Engineers. I have a question. Can you hear me?
Yeah, go ahead, Dave.
Why did you guys use radiant ceiling panel rather than radiant floor heating and cooling? Was it just because it was an existing building, or was there another reason for that?
Probably the major reason is you would have to top the floor and leave it uncarpeted, which would be an acoustic concern. And then once you top a floor, then you have to start adjusting all of the doors out into the cores in order to adjust for that. So in the end, that was one of the reasons. The other reason is you can get about twice as much output per square foot out of a radiant panel than a floor. So it's a little bit more friendly for renovations and small cellular spaces. Radiant floors, although they're somewhat self-regulating, don't provide as good a zone control as quickly as overhead radiant panels.
Thank you.
Sure. Good question. Any other questions? It was that clear? Unbelievable. All right, I'll hand it back over to you, Sam.
Thank you, Tim. That was an excellent presentation. Thank you all for attending the ASHRAE meeting.
Thanks, Sam.
And if any of you want to send me an email or a question or whatever, I know I didn't leave it on the presentation, but Sam's got my email if you guys want to follow up later with any questions.
So as Sayan mentioned, we are still looking for volunteers for the e-week student competitions. We're doing that online this year with the students picking up the materials. So if you have time available, please contact Mac Campen or me. So thanks again.
Okay, I'm going to exit now. Take care, everyone. Stay warm.